All right, so here's the video I promised because I won't be in school tomorrow. So, anyways, we last time we had started rough fluids in motion, so i.e. dynamical fluids. Just to recap what we talked about last time. So again, all this means is that my fluid has to be moving relative to some container. The container itself just can't be moving. That's not what we call fluids in motion. So the fluid has to be moving through some sort of container, meaning that we're going to look at the streamlines that are going through it. And then again, we're comparing the difference between a real fluid and that of a idealized fluid. So in this case, again, the real fluid is the bottom picture. So again, we have some sort of viscosity, which is basically kinetic friction, which is acting more on the side, so slowing down the motion of the fluid. So meaning it's going to have the greatest speed towards the middle and then taper off to the sides. Unlike that of a idealized fluid where there's no viscosity, so all the fluid lines move exactly the same. Other thing is when I put in obstruction in there, so again, the top one here is now the idealized. So in this case, my fluid just goes around the obstacle, but my lines always continue moving in exactly the same direction that we're moving. This is what we call steady flow, which is also known as laminar flow. So in this case, again, they kind of bend around, but they never cross each other. So laminar flow means that the lines cannot cross. So our streamlines here can't cross. As opposed to our realistic situation, which is now the bottom one. So in this case, we can get turbulence, which means that our field or our streamlines here are going to start crossing each other. That's what's happening in this area here, which is basically turbulence. So as this thing comes in, they're getting all crossed up. So that's what we call unsteady. So in this case, the streamlines cross each other, mostly just due to turbulence here. So good. So those are so far our things. So real fluid is again viscous, has kinetic friction, unsteady, where the excuse me, idealized is non-viscous, so no viscosity, steady, so it has laminar flow again. And another thing is for a idealized, this thing has to be an incompressible fluid. Mostly just in the fact that it can't change volume, so its volume doesn't change. That'll be important in the next part. Well, in a real fluid, of course, it doesn't have to be. You can have air and other things like this, so it doesn't have to be incompressible. Last thing is, what happens if I have an object which is floating inside? So let's say here I have an object which is floating here. So what's going to happen then is this object is just going to follow this path here and then just move around here, which means that for the most part, it's just going to move around, which means that there is no rotation. Um, and then in this case, when I put an object here, it's going to move again along this line, but now it's going to get stuck in like a little pool here. So it's going to start spinning around its own axis. So in this case, it build up an angular velocity around its own rotational axis. And this is what we call a rotational. So in this case, this guy is a rotational, which means that again, the object rotates about its own axis. As opposed to in the idealized, this guy's just going to move through, so there is no rotation about its own axis. So this is what's called irrotational, means that there is no rotation about its own axis. So beautiful. So in this case, again, our idealized fluid, then this is going to be our assumption moving forward. So our idealized then is it's going to be again incompressible. Oh, I'll put the I in there. There we go. Compressible. It's going to have what? Steady flow. Going to be non-viscous and irrotational. So about as simple as possible. Otherwise, if it's a realistic ones, there is no algebraic form to look at them because turbulence and things like this is ridiculously hard to talk about. And most of the time has to be talked about in a case by case situation, which basically means that you have to write a computer program to basically analyze it, which means there's no set way of actually looking at it, which is why we're going to focus only on the idealized fluid here, just to make it something more tangible, something we can actually write in terms of mathematical expressions. So good. So first thing we want to look at is what happens if I have a fluid which is flowing from in a tube, which flows from, say, one cross-sectional area to another cross-sectional area. So basically meaning that, okay, my cats are here breaking stuff. Anyways, so here is my original tube here. And let's say this thing has a cross-sectional area of A1 at this, let's talk about this point here, point 1. But again, since it's non-viscous, it doesn't matter where we talk about because, again, all my field lines or my stream lines are going to all be the same. And then let's say this thing tapers down to a new cross-sectional area. And this thing now has this cross-sectional area, A2, and let's look at a point here. Let's call that point 2. So in this case, I'm going to have at point 1, I'm going to have a velocity of v1, and then at 2, I'm going to have a new velocity of v2. So ultimately what I want to know then is how does my velocity at 1 compare to my velocity at 2, right? Now, let's talk what's going to happen. So let's say we're going to have some time frame of delta t. We're going to look at the same delta t over here, okay? And then in that time frame of delta t, so let's say that all the fluid that is initially here at the cross-sectional area then is going to move forward by some amount. Let's call that x1, which means that it's going to sweep out this section here. So now it's going to move forward to this particular location. Okay? Now, what do we know? We know that this thing's going to sweep out a volume, where this is going to have a volume, let's say, V1. Okay? In the same manner of time, let's say that, in this case, we draw in green, all the fluid that's initially here at the initial time, then will go to this location here, meaning it's going to sweep out its own length of x2 as it moves forward here. So that this is going to sweep out some particular volume, where that volume in this case then is going to be simply V2. Now, since we're dealing with an incompressible fluid, what we know in this case then is what? The two volumes must be identically the same because that's what your incompressible means. So these two volumes have to be the same. So all this means then is that the volume swept out volume 1 must then be exactly equal to the volume swept out 2 because the time frames is exactly the same. So let's write this down. So what do we know? We know that volume is the same thing as the cross-sectional area times the distance. So I'm going to get an A1 x1, then it's going to be equal then to A2 times x2. Right. Now, since the first one is moving with a velocity of v1, that means the total distance it's going to have then is going to be v1 times delta t, where the second one is moving at a different velocity, so that's going to be v2 times delta t, just using the second kinematic equation where it's moving at constant speed, so there is no acceleration in this case. So let's write that in. So I'm going to get an a1 v1 times delta t is then equal to a2 times v2 times delta t. But the delta t's are the same. So what this tells me then is that what? A1 V1 must then be equal to A2 times V2. So this tells me a couple things, but the first thing it actually tells me is that since this thing, A1 times V1, has to be equal to A2 times V2, what that means if it tapered down to another cross-sectional area over here, let's call that A3, then the velocity V3 must be times A3 must be equal to the A2 times V2, which must be equal to A1 times V1. So this is what we call the continuity equation, which is also known as the volume flow rate. So in this case, what we have then is that the area times the velocity must be equal to a constant at any point. So this is what the volume flow rate or the continuity equation simply says, is that the area times velocity must be equal to a constant. Now, going back to my original question, what this says then also is I can relate then the velocity at 2 to the velocity at 1 by simply then the ratio of the two areas. Right? So that's what the thing says. So ultimately what this says then is what? If I go back to my original A times V is equal to a constant, what this thing says then is what? If A goes up, V has to go down to preserve the fact that it has to be a constant, or if A goes down, V then has to go up. Right? So ultimately what this means then is let's consider a garden hose. So let's say you got a garden hose. So here's your garden hose. Here's the opening for the garden hose. And let's say that it's just the garden hose by itself, and then the water comes out. So here's the initial velocity of the water, which means that the water is just going to kind of trickle down. Right? At some small initial velocity. So this thing's just going to go under parabolic motion and then fall some small distance of, let's call that little d away. Right? But now, if I put my thumb over part of the hole, so that now here's my thumb, blam. So in this case, I'm now going to cover the part of the hole, which means I'm restricting the size of the area. So what happens in this case then is I increase the velocity, which means that now all the fluid which is coming out has a greater velocity, which means it's going to travel a much greater distance of now capital T, right? So this is how if we want to spray something further in our backyard, or you want to spray one of your friends or something, if you simply let the garden hose run, it's not going to go very far. But if you put your thumb over part of the hole and you restrict the size of the area, then the water comes out much faster, which means you can spray further. And now you can spray some flowers that are over here, or your poor friend who's over here screaming as you're stoking them. Ah. So that's all this thing says. So this thing says, again, for the continuity equation, simply the area times the velocity must be equal to a constant. So again, this is our volume flow rate. From here, we can also define what's known as the mass flow rate, where our mass flow rates, oh, sorry, I should go back to here for a second. Sometimes this is also called Q. It depends. Sometimes it's called Q sub V for the volume flow rate. But we can also define what's known as the mass flow rate. So this one comes from the fact that, remember, that mass is equal to the density times the volume. So in this case, all this means then is since the area times the velocity times the time is equal to the volume, then that means the mass is going to be equal to the density times the area times the velocity times the time, which means then that's what? Our volume flow rate then simply becomes the density times the area times the velocity must be equal to a constant. And since this is all continuous fluid, that means the density must be constant. So in this case, the density is equal to a constant, mostly because it's, again, incompressible. So if it was compressible, you would be able to change the density. Because again, if you think about air, right? If we squash air into a small little volume, then the density goes way up. But if you let it go out and fill up an entire room, in that case, the density goes down. But in this case, since it's incompressible then keeps a fixed density, which means this thing then is still equal to a constant, which again is what we call the mass flow rate. So either way you really want to talk about it, but we have either the mass flow rate or the volume flow rate, which then says the area times the velocity is simply equal to a constant. Right? Sometimes this thing is also known as the flux or the volume flux. And we'll learn more about that next semester. We'll talk more about that. So good. So next thing to talk about is what happens if it changes cross-sectional area and it changes height. So for example, so let's say, again, here is my original cross-sectional area. So let's call that A1. Again, let's call this some point E1 here, point 1. And let's say my tube starts off here, and then it's going to increase height. It's going to also change the diameter or the radius of the cross section, right? So it's going to say taper down so that it decreases size, does something like this, right? So this has area A2, and let's call this guy point 2 over here. And let's say our reference point, I don't know, somewhere down here. So this is our reference point, so that this is at a height of, let's call that y1 above the ground, and let's call this some height of y2 above the Right? So if you think about it, this is a way that you, for example, can get water when you wash your hands in an upstairs bathroom. So you're pulling it from the ground, and then you bring it all the way up to the top. So good. So we know, again, this is going to have some velocity in this direction. So let's call that V1. And then over here, we're going to have some other velocity. Let's call this guy V2. Okay? So we know how, if they're on the same line, these guys were to relate to each other. That would just be the continuity equation. But now, since we have a change of height, we now have to take that change of height into account. And we're going to do that by using conservation of energy. Talking about conservation of energy. So conservation of energy, as always, says that our change in kinetic energy plus our change in potential energy, which in this case is gravitational potential energy, is equal to the work done by the non-conservative force. Now, let's deal with the left-hand side first. So let's say this is 0.2 is my final position. And then here, I'm going to have 0.1, which is my initial position. So kinetic energy wise, we know it's still moving. We're going to have some volume, which is swept out just like before. So we're going to have some mass of fluid inside of here. So that's going to be the mass. Call that mass. And then here, this is also going to sweep out some amount of volume, which means, again, there's going to be some sort of mass here. So let's again call that mass. And again, since it's incompressible, all this is going to happen in the same time frame of, say, delta t, which means the two masses are the same. So my final kinetic energy is going to be 1/2 the mass times then the velocity v2 squared minus then 1/2 the mass times the velocity v1 squared. Now, we also have a gravitational, so my final gravitational potential then is going to be plus mgy2, because again, we have the mass, and that's going to be some height, y2 above the ground, minus then my initial, which is then mgy1, and all that's going to be equal to the work done by the non-conservative force. Now, let's go a little bit further. So is there a non-conservative force? Well, we can rationalize and say, well, yes, there is, right? Because if I only turn on water, then what's going to happen then is the water is not going to move beyond a certain point, right? So if this has a certain amount of kinetic energy, it's only going to move to a certain height. Let's say it only has enough kinetic energy to make it to this point, right? Which means I'm never going to get fluid all the way up to the top. So what we're going to have to do then is basically hook it up to a pump, right? So let's say this is our pump, which means the pump then is going to try to push the water, which means I'm going to get a force in this direction. Let's call that the force F1, which is going to have to push all this fluid all the way up to here. Okay? So in this case, we have a force, which is a driving force. And since this thing has a displacement, let me do that in red, I guess, here, in this direction. So this is going to be my x1 again. What happens then is that this work here is going to be a positive work. So in this case, we're going to get the work from force 1, which will simply be F1 times x1 because they're in the same exact direction. Now, great. Now, what about over here? So let's say initially I have some fluid in this spot here. So the original spot at which I said this thing is going to move. And excuse me. So now I'm going to try to push this fluid up into here into that particular position, which means that we're going to get a force backwards onto this fluid, because if you think about it again, it's like pushing one block into another block. So the original block that you're pushing against is going to say, hey, I'm here, you can't move past me. So you have to move me out of the way, which means I'm going to supply, by Newton's third law, a force back onto you. Which means in this case, we're going to get an additional force, which I'm going to call F2, pushing backwards in this case. But again, we're going to move it forward, which means that, let me do this color, your X2 is actually in this direction, which means they're in opposite directions, which means that in this case, our work 2 is then going to be negative because we get a cosine of 180 degrees of then the force F2 times the distance 2. So the work done by the non-conservative force is simply going to be equal to the sum of these two works. So it's going to be work 1 plus work 2, which is the same thing then as the force 1 times x1 minus the force 2 times x2. So now putting that into our conservation of energy, this thing says that our 1/2 of the mass times final velocity squared minus 1/2 the mass times the initial velocity squared plus the mass times g times y2 minus the mass times g times the height 1 is then equal to F1 x1 minus F2 x2. Now, as, excuse me, it's very dry today. As you guys talked about in class when it came to things like Pascal's principle, when there's a force here, or at least there's a force, there has to be a pressure, which means that there's going to be a pressure on the walls of this thing as it's trying to move. So I'm going to get a pressure here. I'm going to get a pressure P2 here and a pressure P1 here. And remember that pressure is force times area. So I'm going to rewrite each one of these two forces. So F1 then is going to be equal to the pressure P1 times the area A1. And then F2 is going to be equal to the pressure P2 times the area A2. So let's plug that in. So the right-hand side then is going to become equal to P1A1 times X1 minus then P2A2 times X2. But we know from the previous slide that A1, or at least A times X, is equal to the volume. So this is going to be then equal to the pressure P1 times the volume V1 minus the pressure P2 times the volume V2. But again, since we're dealing with incompressible, that means the two volumes are the same. So I'm going to rewrite this then as simply P1 minus P2 all then times the volume. Now, finally, we also know that, again, mass is equal to the density times the volume. So let's rewrite this in terms of density and then divide out the volume. So let's do that in 2 steps. Kind of see what's going on here. Let's use that green color. So finally, we're going to get then is over here 1/2 the density times the volume times V2 squared minus 1/2 the density times the volume times V1 squared plus the density times the volume times G times Y2 minus the density times the volume times G times Y1 is equal to the right-hand side. So now from here, back, what you can see then is all the volumes are simply going to cancel. Let's get rid of all of our volumes here. Cancels with this guy. So finally, at the end of the day, we're going to get 1/2 rho V2 squared minus 1/2 rho V1 squared plus rho GY2 minus rho GY1 is equal to P1 minus P2. Now again, the pressure here is the pressure that it's feeling on the walls here. So good. All we're going to do then is, since I have 2s and 1s, we're going to get all the 2s on one side and all the 1s on the other side. So in this case, I'm going to, on the left-hand side, since all the 1s involving 1 are negative, I'm going to bring it to the right-hand side. And then for the right-hand side, since the P2 is negative, I'm going to bring it to the other side. So finally, we're going to get then is that P2 plus 1/2 rho V2 squared plus rho GY2 must then be equal to P1 plus 1/2 rho V1 squared plus rho times G times Y1, sorry. Or what this ultimately tells me is, since it's at the values of these things at 2 must be equal to the values of them at 1, that means that the whole thing must be equal to a constant. Finally, what I get then is that the pressure plus 1/2 the density times velocity squared plus the density times G times the height must be equal to a constant, just like we said with the continuity equation. This is what we call the Bernoulli's equation. So Bernoulli's equation is the general form of how a fluid works in motion. So when it changes height and it changes pressure and it changes velocity. So this is Bernoulli's equation. So Bernoulli's equation is actually very, very powerful. So this thing tells us a lot of different information. So first things first, Bernoulli's equation is why things like the Heimlich maneuver works. This is why we can actually sail a boat. This is why we can fly an airplane, as I demonstrate here in throwing the paper airplane. It also, excuse me, tells us things about the velocity and the pressure. So and this will relate back to the airplane here in just a second. So what this thing ultimately tells me is, since this thing is equal to a constant, right, going back to here, what this means then is as the velocity here goes up, the pressure then has to go down to maintain the fact that the right-hand side is a constant. Okay? Or simultaneously, if the velocity goes down, then the pressure has to go up to, again, make sure that this thing is constant. So how does that affect an airplane wing? So if I look at the airplane wing, say basically from the side, so let's say here's my airplane wing, it does something like this. What this basically means is to keep the airplane up, I need an overall net upward force, my net upward force, right? Now we know though is that the air pressure on the bottom is making a force this way. This is my F bottom. Simultaneously, we have a force down here, or pushing downward from the air on the top, right? So ultimately, the net upward force then has to be generated by the difference between, or the sum of these two, which means that my F bottom must then be bigger than F top. Otherwise, the net force won't be upward, and then all I'm going to do is crash, right? Specifically also since they have an mg in this direction, so I have an extra force pushing downward, which means that as long as this thing is flying at constant height, in this case, then the bottom force has to be then equal to the top plus then the gravitational. Or ultimately, if we assume the areas are the same, this then tells me that the pressure on the bottom must then be bigger than the pressure on the top. Right? Now, using Bernoulli's equation, that then says is since the pressure on the bottom is what? Higher, that means that the velocity of the particles moving under the wing, v bottom, must be less than the velocity of the particles moving over the top of the wing. Well, that v top. Right? So in this case, we know is that v top must be bigger than v bottom, because again, from Bernoulli's equation, we have to have then that the higher the velocity, the lower the pressure, and the lower the velocity, the higher the pressure, to make sure that this thing actually flies. And this thing also tells us that, again, what has to happen is when there's more velocity, again, there is more lower pressure, which means in this case, I can actually use air to keep a ball above a tube, because the fact that, again, in the center of the tube, we're going to have a lot more velocities, which means the pressure is smaller. Towards the outside, there's less velocity, which means the pressure will be bigger. And then outside of that, where the fluid is basically not really moving at all, it's going to have even a bigger pressure, which means that this thing then is going to mostly sit in the middle, might wobble back and forth, which you'll see in this video. But that wobbling then will always push it back to the position of lowest pressure. So turns out that objects always want to go from a high pressure to a low pressure. So objects always want to move from high pressure to a low pressure. This is also the way that wind works. So basically, when wind, you get a high pressure system here, and then you have a low pressure system over here. And then the particles that are in the high pressure don't want to be in the high pressure, they want to be in the low pressure. So as they move from here to here, this is actually what creates wind. So great. So this is Bernoulli's equation. So let's do an example of Bernoulli's equation, kind of get a better idea of how this thing actually works. Actually, I'm going to do two examples. So the first one is that we're going to have a rain barrel. So let's say here's our rain barrel, something like this. Right. Guy's nice and big. Beautiful. And then towards the bottom of the rain barrel, we're going to then put in a spigot. So here's my spigot. The spigot then is going to be some small cross-sectional area here. So this one's going to have a large cross-sectional area. So let's call that A top. This guy's very large. And then down here, we're going to have A bottom. And then we're going to have that's what A bottom is much, much less than A top. That'll become important here in a second. So good. So we want to know is a couple things. First of all, if I have this thing is filled all the way to the top with fluid, then I'm going to get a velocity out here where this is some height of, let's call that 0.8 meters below the top. We're going to get a velocity coming out here. So what we want to know then is as the fluid is coming out, how far is it going to hit from the bottom of this guy? Or equivalent, just how fast is it? not worry about how far it goes. But basically, we just want to know how fast is it going. Okay? And then this is part A. Oops, color. That's like we just want to know how fast is it coming out. Part B now is we're going to have the spigot now pointing upward. I'm going to turn the spigot so it's pointing upward. And now we want to know is how high, based off the velocity at which it comes out, is my fluid going to reach before it comes to rest. All right. And let's say this is all happening in air. So out here, this is atmospheric pressure. And then over here, this is going to end in atmospheric pressure. Okay, so let's call the top 0.1, and I'm going to call the bottom here 0.2. So we now know Bernoulli's equation says that the pressure at 1 plus 1/2 the density and the velocity at 1 squared plus plus the density times g times height y1 then must be equal to the pressure at 2 plus 1/2 the density velocity 2 plus then the density times g times y2. Now, in this case, what else do we know? So we know that, let's take this as our y is equal to 0 location because we know our height is relative to that. So in this case, we know that what? Y2 is going to be 0. And then Y1, I'm simply going to call some height of Y. Okay. The other thing we know is since this thing is open on the top, as atmospheric pressure, P atmosphere. And then when it comes out, it also has P atmosphere, which means the two pressures are the same. So then we can cancel out the two pressures because they're equal to each other. So we finally get then that's what? 1/2 the density times velocity V1 squared plus rho times Gy is simply then equal to 1/2 rho times V2 squared. Now, next thing is we don't know what V1 is, and we're looking for V2, but we know by the continuity equation V1 and V2 are related. So let's use a continuity equation to figure out what V1 is. So my continuity equation says that, again, our area times our velocity is equal to a constant. So in this case, I'm going to get an A1 times V1 is then equal to V2 times A2. A little bit backwards there. Anyways, solving for V1, this says that V1 then is going to be equal then to V2 times the ratio of the two cross-sectional areas. And an A2 divided by A1. Now, in this problem, I didn't actually give you what A1 was, and I didn't give you what A2 was, or in this case, A top and A bottom. But we do have this condition that, in this case, A1 is much, much bigger than A2. So in this case, since A1 is much, much, much bigger than A2, that means I have a really small number divided by a really huge number, which is basically 0. So in this case, the velocity V1 is simply 0, which means up here, it's not doing anything. But down here, it's coming out pretty fast, right? So at the end of the day, what I get is now that 1/2 the density times velocity V2 squared is equal to simply the density times g times y. But now the densities cancel, so I don't care about the density. And now solve this for V2. So finally I get V2 then is equal to the square root of 2gh or 2gy, right? Same thing where we get with simply conservation of energy. So plugging in my numbers, what I finally find in this case then is that the velocity when it comes out is equal to 4 meters per second. So that's part A. Part B now, we're going to take this thing and point it straight upward so that now the fluid is going to come up. And now we're looking for this height here from the ground, where this height from the ground here now is going to be Y2. Okay, Bernoulli's equation then simply says that, again, P1 plus 1/2 rho V1 squared plus rho Gy1 is equal to P2 plus 1/2 rho V2 squared plus rho G times Y2. Awesome. Now, Y1 we know is simply equal to Y, so I'm going to call that Y. We know the two pressures are the same, so again, they're just atmospheric pressure, so these two are going to cancel. We also know that the velocity V1 is simply equal to 0. So let me define exactly what I'm talking about here. So the only thing I'm doing now is I'm calling this now my 0.2, but this is still my 0.1. So instead of calling it bottom 0.2, I'm now calling where the velocity finally is equal to 0. So in this case, this means that V2 must be equal to 0, since that's my second point. So in this case, V2 is also going to be 0. So what I'm left with in this case then is that what? Rho gy is then equal to rho gy2. So the densities are the same, they cancel. G's are the same, so they cancel. And all this tells me then is that y2 is simply equal to y, or y1, which is then equal to 0.8 meters. So why is this the case? So this is the case because, well, by conservation of energy, this thing says that it should make it back to the same height as long as my velocities are both 0. But ultimately, this is also true because, again, going back to the fact that the spigot here is very small, that again, the cross-sectional area A2 is much, much less than A, which means that the velocity of V2 is very large, which means that initially the water which is coming out only has kinetic energy. Now, kinetic energy has to go all the way up to gravitational potential energy, but the original kinetic energy came from gravitational potential energy, which means the two gravitational potential energies have to be the same. Now, if A2, excuse me, wasn't much, much smaller than A1, that means then there would be a velocity V1 at top, which would no longer be equal to 0, which means that now you would have a kinetic energy plus a potential energy is turned only into potential energy, which means it would actually go higher. Right? So it would actually spring way up like this, so that y2 now would be much higher, or at least higher than y1. So good. So that's problem number 1. Let's look at the second problem. So second problem then says that we have a tank of water. So in this case, here's my tank of water. So here's my tank. Good. Where this thing has some cross-sectional area A1 at the top. And then we're going to do is we're going to cut a small hole on the side. So here's my hole. Great. Where that hole then is going to be some height, little h, from the top of the fluid, which in this case is our water. That's at the top. And then the container has a height of capital H. So let's put in some numbers here. So this is, say, 40 centimeters, and then this guy is equal to 10 centimeters. Okay. So that's going to have my fluid then coming out through the little hole here with some velocity v. And now what we want to know is what I started off last time, is this thing is going to undergo projectile motion, which means it's going to hit the ground. And then we want to know, what is this distance of v, right? Or let's call that x. Let's call it x. So what is the position, or how far away from the base of our container here does it hit? So it's going to be part A. So, and then we'll talk about part B and C here in a second. So part A. So part A is, we know that since this thing is projectile motion, we're going to have to use our kinematic equations, which means we're going to look at the x direction and the y direction. So let's put in a coordinate system. So I'm going to use this one. I'm going to use positive y is downward, and let's move this as the x direction. And we know g is going to be downward, which means that our initial height in the x direction, or my initial x position, is going to be 0 plus the velocity times the time, and there's no acceleration here, so I'm going to get a plus 0. And then here we're going to get a y is equal to y0, which is 0, plus 0 velocity, because all the velocity is in the x direction, plus 1/2 gt squared. And again, plus because it's in the same direction as the positive y direction. So from here, what do we know? We know it's going to fall this amount of distance here. So if this thing has a height of capital H and this portion here is little h, then it means this is going to be capital H minus little h. So this thing's going to fall a total distance of capital minus little h, then is equal to 1/2 g squared. We're solving for the time then is going to be equal to the square root of 2 times h minus h, all divided by g. Now, to find the distance x, all we have to do is plug this into there. So finally, we're going to get then that x is then equal to the square root of, so this way, 2 times v squared times h minus h, all divided by g. So this means all we have to do now is find the velocity, v, when it actually comes out. And we can do that by using, again, Bernoulli's equation. So let's say, again, this thing is open to the air. So I have P atmosphere here. And then when it comes out, it's also P atmosphere. So in this case, Bernoulli's equation says that P 1 plus 1/2 rho v1 squared plus rho gy1 then is equal to, in this case, we're going to get a what's p2 plus 1/2 rho v2 squared plus rho gy2. Now, let's call the top part here again 0.1. Call this point here 0.2. So in this case, I'm going to choose actually this position here as my y is equal to 0, just to make it a little bit easier. So that means that y1 in this case is going to equal little h, and then y2 is going to equal 0. And here again, since I never told anything about the cross-sectional area relative to the size of the hole, we're going to take that A1 is much, much bigger than A2, which means, again, our velocity V1 is going to be equal to approximately 0. And we also know since this is equal to P1 and this is equal then to P2, the two pressures are the same, so they're going to cancel. This guy's going to cancel with him. This velocity is going to be 0, and then this height is going to be 0. Okay. So if I call simply V2 equal to V, so let's put everything together. So I'm going to get a rho G little h is then equal to 1/2 rho V squared. So in this case, my rows are going to cancel. So I'll solve this guy now for V. So this thing tells me then that V, or at least V squared, is going to be 2 times G times H. Let's plug that in here. So this now is going to become equal to the square root of 4 times G times H minus H, all divided by G, which means my G's are now going to cancel. And finally, what I get in this case then is that the distance at which it travels away from the base is going to be the square root of 4 times little h times capital H minus little h. Which makes sense. That thing has to go as h squared because I'm square rooting. So that thing has to give me units of meters. Plugging my numbers when I get in this case then is the distance it's going to travel then is going to be 35 centimeters from the base. Let's talk about part B. So part B now, we want to know what? So we want to know at what depth should a second hole be made to give the same value of x. Okay, so what does that mean? That means that now we want to find a location, put it somewhere down here. But let's say this location here. So I'm going to call this, I don't know, height of h prime. Why not? Where now my fluid's going to come out with a different velocity, which means that now it's going to come out faster because it's now further down, so that this thing is also going to go under projectile motion and then hit exactly the same location. Okay. So I want to know at what depth must this take place for this to happen. So our starting position for this one is going to be going back to x here. Okay. So what we want is for this x to be a constant. Now, how would we solve this? So in this case, instead of looking at x, we're going to look at x squared, mostly just to get rid of the square roots, just for funsies. So good. So in this case, what do we have? So we have that x squared is going to be equal to 4 times h prime times h minus h prime. This thing looks close to a quadratic, so let's write it out as a quadratic. So then we're going to get a 4h prime times h. I'm going to write it slightly differently. I'm going to do 4 times capital H times h prime, excuse me, minus 4 times little h primes. That's that guy. And all that's equal to, again, x squared. So I get a quadratic because I have a squared here and a linear term here and a constant term here. So let's bring these other two terms to the other side. So we're going to get a 4h prime squared minus 4h times h prime plus x squared then is equal to 0. Let's use our quadratic equation. So my quadratic is, well, first let's divide everything by 4. So I'm going to write this as 4th. So that way my A is 1 and my B is just capital H. So good. So now I'm going to get that little h prime is then going to be minus B, which is then just capital H, plus or minus the square root of capital H squared, minus 4 times A, which is 1, times C, which is then x squared over 4. So that way my 4s are going to cancel. All then divided by 2 times A, which is then 2 times capital H. Actually, no, not capital H, just 2. There we go. So good. So in this case, then, what do we know? So we now know that because I have a negative sign here, that means that this entire term here is less than the other term, which means I have 2 valid roots. So in this case, I'm going to get then that h prime is going to be equal then to h minus the square root of h squared minus x squared divided by 2. And let's call that guy simply h prime 1. And then I'm going to get h prime 2 is then going to be the positive, which is h plus the square root of h squared minus x squared, all then divided by 2. So good. So let's plug in our numbers. When I plug in my numbers, I find 2 different locations. The first one then is going to be 10 meters, which we already knew. And then the second one then is going to be 30 centimeters sign. So in this case, what this says then is to get this to go that certain distance of x, it has to be drilled either h, the original h, which is 10 centimeters, or now the new h, which is h prime, which is now 30 centimeters. So that means that this total distance here has to be 30 centimeters below the surface to go exactly the same distance. And now finally, one more thing to do, part C. Now part C then wants to know, where should we put our hole so that way we maximize the distance of x? So where should we put our hole? So let's say, I don't know, put it here. So where should this hole be? Let's call this the maximum from here to here. So let's call that y max. So that way, when it comes out, the velocity then is going to maximize the distance this thing is going to make it. So I want to know then, what is x max? Or more specifically, where should I put the hole, h max or y max, to then get the furthest amount of distance to it? Okay. So good. So let's go back to our x expression, and we're just going to go with that guy and then maximize that guy. So from here, we now know x is given this way. So let's go to part C. So again, we know x then is the distance it's going to travel. It's going to be equal to the square root of 4 times little h times capital H minus little h. Okay. Good. So in this case, but again, I want to extremize x with respect to h. Okay, so I want to find what is the maximum, or what height gives me the maximum distance. Doesn't actually ask what the maximum distance is. We could find that afterward. But we want to know specifically, what is this guy? So that means we're going to take the derivative of x with respect to h. Now, because there's a square root here, it turns out that we can actually not look at the derivative of x, but instead look at the derivative of x squared, because the zeros are exactly the same. Right? So where this thing is 0 is exactly the same place that this guy is 0. So all we're going to do is take a derivative of, with respect to h, of 4 times h minus 4 times h squared. Mm-hmm. So that's our square. Excuse me, taking the derivative of this, and the first one, the h, little h, just goes away. So I'm going to get a 4 capital H. And the second one, then I'm going to get a minus. The derivative is going to pull down to 2, so that's going to become an 8 times then h. Right? And since we're extremizing, all this has to be equal to 0. So let's divide both sides then by 8. So that this is going to become over 2. So finally, what we find then is that h max is simply equal to half the height. So all this means then is to get it to go the actual furthest it can possibly go, we have to then put in the hole at exactly the midway point, or 20 centimeters then below the surface, or 20 centimeters above the ground. This is going to be the distance that gives us the maximum amount of distance. So awesome. So these are our fluids in motion. So again, the big ones are the continuity equation, which again is simply also known as the volume flow rates. Also known as the volume flux. So again, this is just simply says that the area times the velocity is equal to a constant. So anywhere along my tube, this product has to be exactly the same. Right? Thing has to be the same, no matter if the cross section decreases or not. The value of that guy has to be the same everywhere. Means again, as the area goes down, the velocity has to go up, and vice versa. And then there's Bernoulli's equation, where Bernoulli's equation simply says that the pressure plus half of the density times the velocity squared plus the density times the acceleration due to gravity times the height above some reference point must be equal to simply a constant. Again, as this one says, is as the velocity goes up, the pressure goes down, or as the velocity goes down, the pressure then goes up. So this is actually used in many cases, but I'll talk a little bit more about this, especially other interesting thing that can happen. But I'll talk more about that quickly on Thursday before we move on. But this is it. This is the end of this chapter. So we have enough now to be able to fully do all the homework. I'm going to talk about something else that we're not going to do any math for, but it's something pretty cool. So I'm going to talk about that, which means on Thursday, then we're going to start working in the last 4 chapters, which again, I'm going to combine into one single chapter, which I'm going to call thermo, but we're going to look at, first of all, temperature and the thermal properties of materials. So we'll do that on Thursday.